Howdy! This is your friendly neighborhood physics teacher here. Now, this would be one of many videos, hopefully not many, several videos, going over the fall final review. Instead of doing one big video, I'm going to do hopefully a couple of medium videos. And how I'm going to break it up is kind of by unit. Hopefully you're looking at your review at this point in time, and hopefully you've done the review before you started watching these videos. Because doing the review and then checking your work is the best way to study. So if you haven't done your review yet, or at least part 1, unit 1 of the review, pause this video and do at least unit 1 before you start this video. And because again, if you do the video questions by yourself and then come back and compare, that's better than just writing down the answer. You'll learn it a whole lot better. So please do that. So right now we're looking at unit 1. Before unit 1, there's a whole entire 2 pages of different things of what you can do, equations, and then knowing variables and units and everything. I'll do all those as it goes with the unit. This unit itself, there wasn't very much, if you remember. It was safety, dealing with dimensional analysis and metric conversions, and the scientific methods. This is what this unit was. A couple of questions we have is, you're looking at unit 1, is number 1, what is the difference between accuracy and precision? So what's the difference between accuracy and precision? Key thing is, so accuracy is if you're on the money. So if the answer is 2.34, you hit 2.34. You hit that answer. You are accurate. So one answer can be accurate. One answer cannot be accurate. So it just takes one answer to be accurate. Have precision or be precise, you have to look at multiple answers. So you would look at some 232, 233, 235, 234, 236. So you'd have to look at multiple numbers to know if you're precise or not. So just having one number, you can't be precise. So this, you're accurate, but you don't know if you're precise because you don't have enough information. Now, looking at this group here, you are precise because you have multiple numbers to look at, and all the numbers are very close together. So you are precise. Now, again, if this is the answer, one of your numbers is accurate. This number would be accurate, but your grouping is precise. I know in on the video before, I used the arrow example. So hitting on the bullseye. So one arrow hitting the bullseye means you're accurate. Or you can be multiple things. So if you, again, have a bullseye, and you've hit multiple arrows, you've hit multiple arrows, you are accurate and precise. Now, you can be accurate and precise. If you go through again, you can be precise but not accurate. Because again, to be accurate, you have to hit the bullseye. But if we do the arrows and you kind of all do at this little tiny point here, if all converged on this point here, you're precise because you're all hitting in the same area, but you're not accurate. So it is possible to be accurate and not precise because you just do one arrow. You can be precise and accurate, so you've used multiple arrows in one little area, but it's able to be precise but not accurate. So your numbers are all around the same area, you're just not hitting on the bullseye. So that's the difference between precise and accurate. Accurate is you're hitting the money, you're getting the correct answer to the dot. Precision, you have to have a group of numbers, and that group of numbers are close together. So now number 2, how do you write a hypothesis? Big thing is an if-then statement. if I do this, then this will happen. So it's an if-then statement. That's what it have to be a hypothesis. If I do this, then this will happen. So that's your hypothesis. You have to have an if-then statement. Next question is, what unit metric base would you use for mass? Mass, you would use kilograms. And then you would do length. Length is meters. And then volume is milliliters. So you have kilograms, you have meters, and you have millimeters. Milliliters. And then, so there we go. So those are your base units. So when you're trying to do metric conversions, these are all your base units. So if you remember our lovely little staircase here, 3, 4, 1, 2, 3. So this one is, remember, kiss her daily because divorce costs money. And then up here you have giga and mega. And then down here you have micro and nano. This right here is our base. That's what's kind of like kiss her daily is all the good. This is the big stuff. This is the good stuff. Kiss her daily. Because is the middle. Divorce costs money. Divorce costs money is the bad stuff, so that's the negative. So these are the positive numbers. It's a positive statement. Kiss her daily. These are a negative statement. Divorce costs money. Again, so this is your base, so it's times 10 to the 0. Then you just go up, times 10 to the 1, times 10 to the 2, times 10 to the 3. Remember, then it jumps up by 3, so that becomes 6. That's 9. So then this is the negative statement, so you go down negatively. Then you jump to 3, so that becomes negative 6. This becomes negative 9. So you will need to do some conversions with your metric staircase. We do have some practice problems here looking at number 6. So looking at number 6, we're going from 6 meters to centimeters. So meters, remember, is a base. So we're going to start here. So 6 meters is a base. And we're going to centimeters. We're trying to get 2 centimeters. If you remember our little exponents, you can just look at your exponents. So meters is a base, so your exponent is 0. And you always subtract. Always, 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 always subtract. Then we look at centimeters. Centi is -2. -2. So 0 minus a -2, a negative, remember, makes a positive. So it's a +2. These are all exponents. These are all exponents. So this becomes an exponent. So you take it 6.0, because it's just times 10 to the 2. That's all you're doing. This becomes an exponent. So if you remember your numbers here, you can just subtract them, and there's your answer. And it's actually in scientific notation. So that really is our answer. Now, if we go so that's A. Let's jump down to C. C, we're going from 14 grams. We're trying to figure out how many kilograms that is. So grams is a base. Grams is a base, and we're trying to get to kilograms. So grams is 0. Always subtract. Kilograms is 3. So it'd be 0 minus 3 gives us what? So that gives us a negative 3. Again, these are all exponents, so you do 14.0 times 10 to the negative 3. Now, this is not in scientific notation. The reason is because right up here, to be in scientific notation, you need one number in front of the decimal. You need one number in front of the decimal. So we need to move the decimal 1 over. We need to move the decimal 1 over. Now, to know if you're adding or subtracting, if you're making the number smaller, so we're making the number 1.40, the number was 14, we're making it 1.40, we're going to end up adding how many times we moved. So in this case, we're going to add 1. So it becomes 10 to the negative 2. So that is our answer in scientific notation. And then we're going to jump down to E. E is talking about 130 milliliters and how many liters that is. So milliliters, if we go up here, milliliters is negative 3. Liters is a base. Liters is a base. So we do minus 0, and that equals negative 3. Again, that is an exponent. So you just do 130.0 times 10 to the negative 3rd. Now again, this isn't in scientific notation because there's not one number in front of the decimal. So we have to move it 2 times. So that becomes a plus 2. So our answer becomes 1.30 times 10 to the negative 1. And that is our answer. I was looking at the review. I realized that I answered this question incorrectly. These are what we measure them in. Our base units are actually just grams and liters. So I was answering what we use in physics to measure it in. So it is just grams and liters. I do apologize about that. I was going back through my questions and I was like, I answered the wrong question. So that's metric conversions. I'll give you a hint. On your conversion chart in the middle, it has most of your stairwell for you. So look at your conversion chart. If you forget, it does have most of your stairwell for you. Look at your conversion chart in your chicken duck. That's the exact same chart you'll be given on the test. Let's go back and look at B and D. B and D are dimensional analysis. B and D are dimensional analysis. So now remember, for dimensional analysis, you put what you're given up here, and you have to work your way through. So remember, we do not want day. We do not want day. So day has to go down here so it cancels out. But we're wanting seconds. I don't know how many seconds are in a day, but I know how many hours are in a day. So 24 hours in one day. This day cancels, and this day cancels. So we're just left with hour. But we don't want hour. So hour again gets shunned to the bottom. If you look on your conversion chart, it tells you how many seconds are in an hour. So you know how many seconds are in an hour. Again, this cancels because of this. One on top, one on bottom. They cancel. So for 1 hour, there's 3,660 seconds. Now, nope, it's not a 6, it's a 0. I was like, wait a minute. So 3,600 seconds. Now, we're left with seconds. That's what we want. We're left with what we want. We want seconds. Now we just need to get our numbers all together. So you multiply across the top. So 1 times 1, 3,600 just gives you 3,600 seconds. Now we multiply across the bottom. 24 times 1 just gives you 24, and there's no unit. So now you just do 3,600 divided by 24. And you get 150 seconds. That's your answer. You're done. Now let's look at the next one. The next one is in miles per hour. Next one's in miles per hour. I've given you 25 miles per hour to be exact. So 25. If you remember, per means divide. So I gave you 25 miles per 1 hour. 25 miles per 1 hour. We can just focus on one at a time. So let's focus in on the miles. We don't want miles, so miles get shunned to the bottom. If we look on your conversion chart, there's not a direct miles to meters, but there is a miles to kilometers. And for 1 mile, I'm going to make sure I have that. I'm looking at my conversion chart to make sure I have it right. So for 1 mile, there's 1.609 kilometers. And that mile cancels out. But we don't want kilometers, we want meters. So kilometers gets shunned to the bottom. We want meters. So for 1 kilometer, there's 1,000 meters. And there's multiple paths to take. You could go from miles to feet, feet to meters. You can go from miles to yards, yards to meters. And I think you can even go from miles to inches, inches to meters. There's multiple paths you can take. Doesn't matter. You're still going to get around the same answer. Your kilometers cancel. But we want meters. That's what we want. But we still have hours. So hours is on the bottom. We don't want hours. So to cancel it out, it has to go on top. And again, we want seconds. So for 1 hour, there's 3,600 seconds. Hour on bottom, hour on top, so it cancels. And we wanted seconds. So now again, we just multiply across the top. So you do 25 times 1.609 times 1,000 times 1, and that gives you right with the wrong thing. So it gives you 40225 and meters. Now we just multiply across the top. 1 times 1 times 1 times 3,600 gives you 3,600 seconds. And that's what we wanted, meters per second. Now we just divide. So we divide 40,225 divided by 3,600, and you get 11.17 meters per second. There we go. Now, on the review, questions 7 and 8 say, look at the Kool-Aid question. That is on test 1, looking at your Kool-Aid question. And it says also look at your Shazam question. I would highly suggest you to look at those. And I'll even do them for you right here. But don't just look at those. I would, again, highly suggest you to look at your exam. Those questions might pop up again. Just maybe. Just maybe. So let's go through, and I will do the Kool-Aid question and the Shazam question for you. I'm not very sure what test I am looking at, so of course the numbers are going to be different, potentially different from your exam, but you'll at least get the idea. So it says Catherine made 25.29 liters of Kool-Aid for a back-to-school party. Her guests drank 17,350 liters of Kool-Aid. Milliliters of Kool-Aid. Catherine has blank liters left. So the givens are 25.29 liters of Kool-Aid. That's what she made. And then to know how much she drank, to know how much, and said, her guests drank 17,350 milliliters. So know how much is left, we need to subtract them. But we can't subtract them right away. They do not have like terms. And it wants the answer in liters. It says how much liters is left. So we need to convert the milliliters to liters. If you go to your conversion chart, look in the middle, it kind of gives you the order. You just have to know the number. So you need to know that milliliters is milli is -3. Liters is a base. So you're doing -3 minus 0, and that gives you -3. Again, that is an exponent. So you're getting 17,350 times 10 to the -3. If you want to move that around so you can actually subtract, you're just move that -3 just means you're moving it 1, 2, 3 to the left. So that becomes 17.35 liters. So that's technically in liters. We're just moving it so it becomes easier to subtract. So she made 25.29 liters. Her guest drank 17.35 liters. To figure out what's left, you just subtract the two. Subtract 17.35, and there is 7.94 liters left. And that would be your answer. If you're putting it into scientific notation, 7.94 times 10 to the 0th power, because we did not need to move the decimal because there's already one number in front of the decimal. The other one, remember, I tell you to look at your Shazam from the first test. And again, I'm going to say it again, I would look at all of your questions, but these are just 2 good practice problems to do. It says you're hanging out in Lake Belton taking pictures of nature. At a distance, you see Shazam flying at you at 26,000 miles per hour. Shazam flies blank meters per second. So he's flying blank meters per second. So this is your given. Meters, miles per hour. Miles per hour. And we're trying to get it into meters per second. So remember that per means divide. So miles goes on top, and that we do that in 1 hour. So that's per hour. So in 1 hour, he has traveled 2,600 miles. That's what that means. But we need to get it into meters per second. So we're going to focus in on the miles first. We don't want miles, so miles get shunned to the bottom. And again, looking at your chart, there's multiple paths to do it. So let's do it in a different path. Let's go from miles to feet. So for 1 mile, we have 5,280 feet. Miles cancel because we don't want miles, but we really don't want feet either. So feet need to get shunned to the bottom because we want meters. If you're looking at your conversion thing, so for one foot, you have 0.35 or 0.305 meters. Our feet cancel. and you're left with meters. That's what we want. We want meters. But we still have this hours. We don't want hours. Hours need to go away. Hours on the bottom. To cancel it out, it's got to go on top. But we want seconds. On your conversion chart, it says for 1 hour, you have 3,600 seconds. Our hours cancel, and we're left with seconds. Now we just multiply across the top, multiply across the bottom, and divide. So you do 2,600 times 5,280 times 0.305 times 1, and that gives you this huge number, and I keep trying to write with my highlighter. So it'd be 4187040, and that's in meters. And now we multiply across the top, the bottom. 1 times 1 times 1 times 3,600. So 3,600 seconds. And you just divide by 3,600. And that's left with 1,163.07 meters per second. If you want to put that into scientific notation, we want one number in front of the decimal. So we move it 1, 2, 3 times. So you get an answer of 1.16 times 10 to the 3 meters per second. There we go. So that is my help for Unit 1. I will see you again when we talk about Unit 2. Again, I highly suggest you to go back and look at old questions. You never know. They might reappear. Have an awesome day, guys. Bye.